Okay, the next section in the book is talking about rational functions. So we talked about polynomials. Um, and, the key things about a polynomial in terms of plotting it are what is the end behavior, what are the x and y intercepts. In calculus, if you take calculus, you'll learn techniques to figure out where the maximums and minimums occur. Anyway, we're not worried about calculus right now. So another class of functions are rational functions, and basically they're ratios of polynomials. So, rational functions are a ratio of two polynomials. In this chapter, we will limit ourselves to where there are no common factors in the numerator and the denominator. What does that mean? Let me just give you an example. So if we had a rational function, and let's say we had x squared minus 1 over x minus 1, and if you factored out, actually, x squared over x squared minus x. So if you factored x out of the numerator, you get x times x minus 1 divided by x minus 1. So this is what we mean by a common factor in the numerator and the denominator, because you might think, well, I can simplify this by canceling those out. But the resulting simplification is not exactly the same as the original function. It's the same except at one point, which is x equals 1. Anyway, we're not going to consider that because that's calculus. How do you deal with that kind of situation? So to plot rational functions, we have, in addition to x and y intercepts, we have horizontal and vertical asymptotes. So that's, we're going to spend a lot of time talking about these two, mostly about vertical asymptotes. Horizontal asymptotes are a value of y which the function approaches as x goes to plus or minus infinity. They may not approach the same value of y. A lot of times they do. For most of our cases they will. And vertical asymptotes are the values of x where the function approaches plus or minus infinity. To look at horizontal asymptotes, we have to look at both the numerator and the denominator. For vertical asymptotes, we really just need to look at the denominator. And where the denominator equals 0, the values of x where the denominator equals 0 is the point where you have vertical asymptotes. And so, as I just said, vertical asymptotes occur at the real zeros of the polynomial in the denominator of the rational function. So the things that we learned how to find zeros of polynomials come into play here. So what will happen is the function will be actually undefined at the vertical asymptotes. So this is what happens when the denominator goes to 0. You get vertical asymptotes. Where the numerator goes to 0 are the values of x, where the function is 0, and that is the zeros of the rational function. So the polynomial that is the numerator of the rational function is used to find out where we have real zeros or intercepts. And to be able to find these asymptotes and intercepts, we need to be able to factor the polynomials that are part of the numerator, that define the numerator and the denominator. So here we have a reasonably complicated rational function. The reason I put it in here is we're not going to plot this at this particular point. We're just going to factor it, factor the numerator and the denominator. So you can hopefully do this by observation in this case, and you can't always. You might have to use completing the square, quadratic formula. but most of the ones we're going to do are going to have a whole number intercepts and zeros, just because it's easier to do. So we have to say what two numbers multiplied together give us -5, but where added together give you -4. So because we have a negative sign here, we know that one of these factors has to be positive, has a positive sign, one has to have a negative sign. Negative sign is a positive, negative. And because the coefficient associated with x is negative, that means the larger of the two numbers that multiplied together give you 5, that has to be negative. So that one has to be positive. So now you can see if I multiply this out, I'll get x squared plus 1x minus 5x, which gives you -4x. And positive 1 times -5 gives you -5. And you do the same thing in the denominator. So two numbers multiplied together give you 3. It's positive. So we're going to add the two numbers together. So we're going to have a 3 and a 1, and they both have to be positive to give a positive result here, or they have to be both negative. So to get +3, these would have to be both positive or both negative. And because this is a positive, then these both have to be positive. So what you can say is that the vertical asymptotes are going to be where the denominator goes to 0. And so we can say the vertical asymptotes occur when x plus 3 times x plus 1 equals 0. And that happens when either one of these two go to 0. So x plus 3 equals 0 is one solution, and x plus 1 equals 0 is the other way to get 0. You can't have both 0 at the same time. So if you solve for x, you'll get x equals -3 and x equals -1. So these are your vertical asymptotes. And then if you look at the zeros, x-intercepts, that's when the numerator is 0. So x plus 1 times x minus 5 equals 0. And that occurs when either one of these is 0. So x plus 1 equals 0, x minus 5 equals 0. So solve for x, you get x equals -1 and x equals 5. So we know you have x-intercepts, or zeros, at these two values of x. So we'll use those later to plot them, but that's the key thing, is that you always have to factor the polynomial in the numerator and the denominator to find the vertical asymptotes and the zeros. Now what happens if the polynomial in the numerator doesn't have any real zeros? So you could have that. I'm going to make up a problem here. We'll assume that the numerator is just a simple 1. But you could have x squared plus 4x plus 16. Okay, so what you would, if you tried to find the real zeros of, oh, that says in the numerator, sorry. So let's switch that around. So I'm going to fix that. So you say you have x squared plus 4x plus 16 divided by x. So this is still a rational function. The polynomial, the denominator is pretty simple, y equals x. And what you would find out is that there are no real zeros associated with this, with the numerator. And therefore there would be, basically you have no x-intercepts in that case. So if you can't factor this, now how do we know we can't factor it? Well, one way is if you use completing the square. So you want to do, what you want to do is set that equal to, just rewrite that. And if you take x squared plus 4x and take this 4, divide by 2, square it, you get plus 4. And if you move this to the other side, let's set that equal to 0. If you move that to the other side, that becomes negative 16. So I've added 4 here, so I've got to add 4 again. So add 4 to both sides so that I can make that into a complete square. And then I have negative 16 over there. So this left-hand side will become x plus 2 quantity squared. That's a perfect complete square. And this will become negative 12. Well, when you try to solve for x, you take the square root of negative 12, which you would end up with imaginary numbers. So this has no real zeros, and therefore there are no x-intercepts. And the same thing you could say if I just flip this thing over, x divided by x squared plus 4x plus 16. Again, the denominator has zeros, but they're not real zeros, they're imaginary. And because of that, this rational function would have no vertical asymptotes, even though there is a polynomial in the denominator. So you can't always assume that the numerator and the denominator are factorable. They may not be factorable in terms of real results. Okay, so the way we're going to do this is we're going to look at rational functions of increasing difficulty to demonstrate how you go about finding the important characteristics of a rational function so that you're able to plot them. And just to let you know, this lecture is going to be broken up into multiple parts just because there's a lot of material. So 1 over x, it's a rational function. What's the polynomial in the numerator? Y equals 1. What's the polynomial in the denominator? Y equals x. So we've actually looked at this before. We call this the reciprocal function. And we know that it has a vertical asymptote at x equals 0 because that goes to 0. So let's look at the next page. Okay, just wanted to see what I had as far as material. There's actually a list of things you do to find to plot a rational function, but because these are fairly simple, I'm going to just look at them rudimentary here right now. So we know that because there are no values of x where the numerator goes to 0, we know we have no x-intercepts. We also know that we have a vertical asymptote at x equals 0 because that will make the function undefined. So as you get closer and closer to 0 from one side, from the positive side, you go to positive infinity. If you come to this value of x equals 0 from the negative side, you'll have a asymptote that goes to negative infinity. So if we plot that, you can see it here. So we've drawn a green vertical line. That's our vertical asymptote. So at that point, x equals 0, the function is undefined. Any value of x greater than 0, you're going to have a positive value. And any value of x less than 0, you're going to have a negative value. And as you approach this value of x equals 0, you either go to negative infinity or positive infinity. But we can't say that the value of the function equals either plus or minus infinity for reasons we'll talk more about in calculus, hopefully, which you'll take. You'll also notice that as x gets large in the positive direction, you can see as x gets large, this becomes a fraction that's becomes smaller, 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 and as x goes to infinity, this ratio will approach x equals 0. It will never actually equal x equals 0. And for the same reason, on the other side, it will approach 0 from the negative side. It will never equal 0. That's the whole concept of limits, which you'll get into in calculus. Okay, so let's make this slightly differently. So this is a reciprocal function, and from chapter 1 we can think about it being this function translated in the direction positive 3 units because you always have x minus h. So minus h is 3, so that means it's going to be shifted to the right 3 units. Another way of looking at it in terms of rational functions is we know that the denominator goes to 0, equals 0, when x equals positive 3. 3 minus 3 is 0. So we know that we have a vertical asymptote at x equals positive 3. And therefore, you're basically just shifting over the original reciprocal function by 3 units in the x direction. So you approach positive infinity here and negative infinity here. The horizontal asymptotes are x equals 0, and it's still x equals 0. Okay, so now what we're doing is we've got two factors. If I multiply this out, I'll get 1 over x squared minus 9. So if I was given this function originally, I'd say, okay, well, I've first got to factor it to find out what values of x. The denominator equals 0. And at those points, I have vertical asymptotes. The question might be, do they go up or do they go down? Which ones go up, which go down? So this is what it looks like. Again, you'll notice that the numerator never goes to 0. So I know that this red line, which is the function, never crosses the x-axis. It can approach the x-axis, but it can't cross the x-axis anywhere. So here it approaches y equals 0, here it approaches y equals 0. The interesting thing is that instead of on the left-hand side approaching negative infinity, the asymptote, we approach positive infinity. And there's a couple of ways you can think about this. If x is greater than, if x is large, then large minus 3 is still positive, and large plus 3 is positive. So these both are positive. So I know that when x is, in this case, greater than 3, these two terms are going to be positive. So I know the fraction is positive, so therefore I know that the function has to come above the, has to be above the x-axis. And therefore, because it's above the x-axis, it has to stay above the x-axis because there's no x-intercepts. So, and I know because of that this has to approach positive infinity. There's no way to cross over because this doesn't allow it. Now, you might ask the question, well, could I have the function approach positive infinity from the left-hand side? And the answer is no, and that only happens the only time you have a case where they approach the same direction at a vertical asymptote is when they have the same root. So if I had x plus 3 times x plus 3, then yeah, it would do that. But in this case, I have x minus 3 and x plus 3. So you always, when you have a single root in the denominator, in this case, single root of x equals 3 and x equals negative 3, you always have the vertical asymptote switch from being positive to negative infinity. So I would know that this has to come from negative infinity. I know that it can't cross the x-axis, so it has to stay below the x-axis. If you set x equal to 0, then you know exactly where it crosses the y-axis, which would be 1. You'd have, if this is 0 and this is 0, you'd have 1 over negative 3 times positive 3, which would be negative 1/9. So the y value, where the function crosses the y-axis, is going to be negative 1/9, which makes sense. It has to be negative. And then as you come over here, as you proceed from right to left, you're going to, again, approach this vertical asymptote, which means it either has to go that way or this way. Well, it can't go this way because you'd have to cross the x-axis. So I know it goes down because this x plus 3 equals 0, which defines this vertical asymptote, is a single root then I know that it has to flip from negative to positive. And also you can think if x were negative, a big negative number, then negative, say 10 minus 3 is still negative, and negative 10 plus 3 is still negative. So negative times negative is positive, so the result has to be a positive. So that also makes sense. So there's a lot of ways you can look at these to know which way these asymptotes go based on whether you use single or double roots. And just looking at in terms of the asymptotes, the horizontal asymptotes, which is what are the values of y when x gets very large in both directions. You can just put big numbers in there and look at the signs to know which side of the x-axis you're looking at. Okay, so now we've got another one that's a little more complicated. So I've added one more factor in the denominator, but it's the same. So you have x minus 3 and x minus 3. So when x equals 3, these both go to 0. So we still have two vertical asymptotes, one at x equals negative 3 and one at x equals positive 3. But what's going to happen is that where we have the double root, the asymptote is going to go in the same direction. So it's either going to go both to positive infinity or both to negative infinity. And again, if you think about it, if these are all big numbers, all big positive numbers, then you're going to positive times positive times positive. So this whole thing's going to be positive when you have a large positive x. We also, again, don't have any x-intercepts. So here's the graph. Let's just put it on one page so we can look at it. So we know this is above the x-axis because when x is large positive, all of these three will become positive. Hence, we start out on the positive side of the x-axis and we continue on the positive side. So we know this has to go to positive infinity. But because these are repeated roots, it turns out that on the other side of the vertical asymptote that it's still positive. So it's positive here, then we move from right to left. We're going to have an x-intercept here, which is going to turn out to be positive, because if you let x equal 0, you're going to have a negative times a positive times a negative, which is positive. Besides the fact that if there are no x-intercepts, once this is the only way you can get to the other side of the axis is to cross a vertical asymptote, which we're not doing, so this has to remain on this side of the x-axis. So we know when we get over here it has to go up. And because we only have a single root at x equals negative 3, we know that it has to go from positive infinity to negative infinity. And then we come down here and we approach x equals 0. And again, there's multiple reasons. One, we're on this side of the x-axis, so it has to stay on this side of the x-axis. Also, if you let x be a large negative number, these three terms will become insignificant at some point. And so you have a negative times a negative times a negative, 3 negatives to give you a negative. So it has to stay on this side. Okay, now what we're going to do is we're going to go back step and put something in the numerator besides x, besides just a constant. So now what we're going to do is I think we're going to talk about, at some point here, we have to talk about the procedure. Let me go find the procedure. So we could keep doing it this way, but I want to take this thing, guidelines, it's on page 168 in the 6th edition. So we can do that here. So that's at a page. There we go. Okay, so the guidelines for graphing rational functions, and we've done pretty much done all these things, but now we're going to follow the 6-step procedure for all of these graphs. And I think I'm going to stop there. So this is part 1 of rational functions.